Okay, great. Right, so it's week 4, and last time we talked about canonical ensemble and study some examples, right? So today I would like to talk about something about about thermodynamics. Since you will have midterm next week, I think it's good to do some examples and for thermodynamics, especially since there are many thermodynamics problems in problem 2, right? Meaning that there will be some thermodynamic problems in the midterm, I guess. So as you will see, many results we obtained in thermodynamics can be derived from statistical mechanics, like from the free energy, partition function, stuff like that. Okay, so by the way, feel free to stop me as usual whenever you have questions. So today I would like to cover 2 kinds of problems. So one is given us the state equation and calculate the entropy and the energy. I will give you several examples, including one of the homework, I think. Another kind of problem is the PV diagram, and you need to calculate the heat and versus the work done by the system in each process, and versus the efficiency of the process, the whole process, right? Okay, so let's start with the first part. So basically, we need to calculate this S and E from some for example PV equal to NKBT for ideal gas. Remember in previous discussion we derived this equation, this P equal to the NKBT equal to V from the partial F partial V, I guess, minus, right? So now, given this result, we need to derive something, some thermodynamic potential. That means it's like a tell you the derivative, ask you to calculate what's the original function. So definitely when you do the integral, you will introduce some constants. Without without actual information, we cannot fix the constants unless you put some physical information into formalism into your calculation. Of course, those constants are fixed if we calculate this kind of S and E from the partition function approach, right? Yeah, so from thermodynamics, the starting point is always the conservation of energy, right? It's D equal to T ds minus P dV, something like that. Yeah, I'm pretty sure you already did this in your homework. So now let's first look at the energy. So we want to calculate it as a function of T and V. So that's actually corresponding to the canonical ensemble, right? If you want to think in terms of the statistical mechanics. So this is a function of T and V. We know what this guy is. Just partial S, partial T. this is the partial derivative dt and partial s partial v fixed t dv, right? And this is dv, this is dv, so we can combine those two terms. This is nothing but the heat capacity, right? CV, because if you fix V, fix V, you will get dE equal to T partial S partial T dt. So dE dt fixed V equal to this guy. This is nothing but CV, right? And this guy, from the Maxwell's relation, this guy is thought partial P, something like that, partial T or fixed V. I think so, right? Or partial, yeah, I think so. So this guy is T minus P. So once we specify the state of state equation, we can calculate this expression. So now we have two equation. One is partial E, partial V, fixed T. We have this one and partial E, partial T, fixed V. We have this one, right? So basically, all the for all the problems, the starting points is like those two equations, and you just need to do integrals and get the expression. The logic is very simple. Right. Similarly, for the entropy, we can have similar stuff. So basically, we have T ds minus P dv. This is I just copy this line. And the last line tells us Cv dt, this line, plus dv minus dv. So this tells us to cancel out, right? Like this. So you would also get two equations. One is partial S, partial V, with fixed T equal to partial P, partial T, V. This one. And this can be evaluated if we specify the state equation. And another thing is like this, right? Any question about this part? Okay, so there's several homework problems, right, in the homework 2 problem set, like this. Yeah, let us do some examples. Okay, so first example, now for the ideal gas, and it's very simple. It's PV equal to N kBT. Let's look at the energy. energy, we only need this one, right? So partial E, partial V, fixed T, give us T partial P partial T, V minus P. And because we know the, state equation, we can evaluate this partial derivative, right? So P equal to NKB T divided by V. Since we fix V, so V is a constant, and take a partial derivative, we get this coefficient, which is NKB divided by V. And combined with this T here, this is nothing but P, right? So this means TV KB V minus P. So this is nothing but P. And this is 0, meaning that our internal energy only depends on temperature. It's independent of the volume. Of course, we know it's only dependent on the temperature, right? And okay, so another equation, differential equation, another condition for this energy is the derivative with respect to temperature. So basically dE dt equal to CV. This tells us, of course, we know for ideal gas, the CV is a constant. It's independent of T and V, right? So it gives us E equal to CV T plus a constant. Mathematically speaking, we cannot determine this constant. Of course, we can say for classical system, we can, it's reasonable that at 0 temperature, there's no motion, no internal energy. So like T 0, E equals 0. So we can set the constant to be 0, something like that. But yeah, that's all we can derive from those two equations. Once give us the equation of motion, the state of equation, we can determine the volume dependence of this energy. Once we specify the the heat capacity, we can determine the temperature dependence on of the energy. And you can do the same thing for the entropy. There will be some constant, and you can argue that for classical system, the ground state is unique, and so meaning that if you set temperature to 0, we would imagine the entropy to be 0. That can help us to fix some constant. But if you derive from the partition function, there will be no problem. Like there's no constant. Everything is kind of fixed. Right. This is also one of the homework parts. For the ideal gas, give the if this state equation asks you to calculate internal energy and the entropy. So here's just a very simple example. So another example I want to do is, just show you it always works. Let's assume the state equation is given in this form. Like A is a constant, T is a temperature, V is a volume. So now we don't know the CV. If we only know this guy, that means we can only determine the temperature, the volume dependence on this energy, right, of this energy. So it's like give you some partial information you want. There's no way to get the whole information of this dynamics. Right? So this kind of state of equation is similar to the force. Like you know, if you imagine this P as the force and the V as the displacement, it's like tell you F equal to some function of X. It's like a Hooke's law, right? It's like F equal to Kx. If we only know this guy, in general, you don't know what is the Lagrange, right? You only know the potential. And it's just the analogy with mechanics. That's okay. So for this, let's write down this partial t. Just make sure I didn't make any mistake. This t partial t v minus p. So similarly, we fix v, meaning that v is a constant. We when we take this partial derivative. So this guy is a3a t squared divided by v, and times t give us 3a t cubed v minus p, and this p is a t cubed v. So we have something like this. If we do an integral over this v volume, we get 2a t cubed log v plus some ft. Right. To be rigorous, I mean, to make sense of this log function, we can add some, a constant v naught, which has a dimension L squared, like a length cube. Something like this. That's all you can we can get if we only know this state equation.
Hey, G. Oh, go ahead, Michael.
I was just going to ask, could you elaborate on that V naught term that you just added in there?
Oh, okay. So here is just a some arbitrary, some constant V naught that make this argument to be dimensionless, right? Because we know the argument of some log function or exponential function must be dimensionless.
So I had a kind of follow-up question on this. In our homework, like a second homework, I think, there were, I think, equation of state or something had like t to the power 1.1 or like 1.2 or something, which also doesn't make sense dimensionally, right?
Yeah, that's true. Yeah, you're right, I think. Yeah.
So how do we make sense of that? Or is it just exercise for a reader?
Yeah, I guess it's just the exercise. Or you add some key factors to, to make it sensible, or I don't know. You're right. Oops. Okay, yeah, I'm going to do that homework actually. Yeah, that's a nice problem. I mean, as a exercise, is a very nice problem. Okay, so let me do that homework. I mean, the logic is the same. You just kind of write down the partial derivative and do an integral. You get the volume dependence, and then you look at another derivative. You get the temperature dependence. There will be some constant need to be fixed. Okay, so let's do another example. That's the homework 4, I think, 4. So let's write down P VA equal to alpha T B. And we know the CV naught. V naught is some specific volume. Right? And A, alpha, B are given. And you can kind of, choose a proper alpha to make the dimension match to size, I guess. Okay. I mean, the logic is the same. So basically, look at the energy. So by doing this kind of examples, I hope you guys know how to solve this kind of problem. So it's very straightforward. Right. Okay, so similarly, since we know the state equation, we just plug in, take a derivative. That's all you need to do. V is a constant, and the T, the partial P partial T fixed V is B alpha times T give us, so B, right? Because now I times T. So minus B minus P. P is this guy, alpha V. So I'm doing here step by step. Like this. Right. Oops. I should fix take a V, right? Yeah, now with the integral for the volume V, we get the volume dependence, which is everyone know how to do this integral. Minus 1 minus A, right? TB plus some function of T. Right? Then another function, sorry, another condition we know is CV naught. Something like this. So we just plug in and determine what is this undetermined FT. Right? So take a derivative with respect to this temperature. We got, so the left-hand side is B minus 1 alpha and V. Okay. Since we set V to be V naught, so it's V naught is a constant, and this is B minus 1 plus. By the way, correct me if I made any mistake. V naught equal to V naught. This is on right hand side. So we know what is F prime is, which is CV naught minus the whole thing.
So I have a question about the heat capacity at this specific volume. So we're still able to get an expression for E at any volume, only given the specific heat at one specific constant volume. Okay.
Yeah, I mean, in general, this CV is also volume dependent, right? Of course, for ideal gas, it's not. It's just a constant. It's some, but in general, it's volume dependent. you don't need to know the what exact dependence on volume. You only need to some specific number, some specific volume. That's enough for determining this kind of a f, as you can see from here, right? What's this? Okay, yeah, it's like this, right? Then you do the integral. This is a full derivative, right? Because this f has only t dependence. What is this? How to do this integral? Okay, so it's b of a. This b cancel with this b, something like this. Oops, plus a constant. So this constant is a real constant. It's independent of t and v. Now we only need to plug this into the expression of energy. Then we determine what is the energy, right? So energy, so we have this guy, and we can combine the first term here with, with this term here. So which is b minus 1 alpha and tb, v minus v naught plus some constant. Okay. If you assume at 0 temperature the energy also vanishes, then the constant is 0. Of course, yeah, we need to assume b is a positive number. Yeah, and you can do similar stuff for the entropy, right? Basically, you also have two differential equations and solve it in a similar way. I don't want to repeat that calculation. So any question about this part? Okay, sounds good. Yeah, it's quite straightforward. Okay, so what's the next thing I want to say? Okay, right, it's a engine, right? Okay, so for engine, we know we have some hot reservoir and some cold reservoir. So the purpose of engine is by absorbing some heat from the hot reservoir and do some useful work, right? Something like this. Right, of course, the energy is conserved. W equal to QH minus QC. And the efficiency is given by what we want. What we want is W, and what we take, which is the QH. So it's QH minus QC, something like this. Right. Right. Okay, so let's look at the example. Instead of considering the Carnot engine, which is everyone know how to do it, let's consider some arbitrary. Okay, so it's a PV diagram, right? By the way, if it's not PV or if it's some other coordinate, for example, PT, whatever, I mean, you can do it in a similar manner. P1, P2. Let's consider this engine. So this 9, those 2 9s are adiabatic 9. Sorry. And so let's call this point A, B, and C, D. So from A to B, the pressure is a constant, and B to C, there's no heat exchange between the system with the environment, and C to D, the pressure is also constant. From D to A, there is no heat exchange between the system and the environment. Right? That's basically the physics of this cycle. And if we know P1 and P2, they are given, and the Warsaw of let's assume it's ideal gas, and the Warsaw we know the CP. Of course, if we know CP, then we know CV, right? They are related. And then we know this gamma, so it's PV gamma equal constant. So just to refresh your memory, this CV is partial E, partial T fixed V. CP is partial E, partial T fixed V. Sorry, fixed, I think it's a fixed P, right? And plus P. And for the ideal gas, they're the same. So the difference is this guy is some constant NKB, right? So if you know CV, you know CP. You know CP, you know CV. Okay, so it's just some side remark. Oops. Okay, so okay, let's consider. Okay, now the question ask you to calculate the efficiency of this engine. I mean, for each process, for example, from A to B, B to C, and C to D, and D back to A, you can calculate the heat absorbed or released by the system, and also the work done by the system on the environment. And for each process, you can calculate those two quantities, right? If you know those quantities, you can calculate everything you want. So let's look at what's this Q and W for each process. So Q from A to B is nothing but CP because it's a constant pressure process, and TB minus TA, right? That's the definition of the CP. Remember, CP is dQ dt fixed P, right? And for the work, by the way, this is a positive number, meaning that in the process of A to B, the system is absorbing heat from the environment. The work done in this process is given by d p dv integral from point A to point B, right? So at this point, let us just leave it like this. By the way, this volume, sorry, this integral from A to B, you can see the volume is increasing, meaning that the system is doing positive work on the environment, right? Meaning that the system is losing energy. So from B to C, it's an adiabatic process. So it's zero. There's no heat exchange. And the work, similarly, let me just write down kind of a formally as this integral. The heat absorbed by the, released by the system from C to D is given by Cp, similar to the process of A to B, D minus C. So it's negative, meaning that the system is releasing energy to the environment. The work is also this expression. By the way, the reason why I leave it like this is because it's more straightforward to write down the heat. If we need the work, then we come back and calculate the work. If we don't need the work, yeah, we just leave it like this. Right? The heat from D to A is also an adiabatic process, so it's zero. Yes. So what is the efficiency? So the efficiency is given by like what I wrote down before. Is 1 minus QC QH. Now what is QC? Remember QC should be this guy, right? QC is the heat released by the system to the cold reservoir. Right? And this should be QH. QH is the energy absorbed, sorry, the heat absorbed by the system from the hot reservoir. So it's 1 minus Cp Tc minus Td. Now you should the absolute value is a QC. It's a positive number. Cp Td minus T. Yeah, any question about this expression? Okay, so I guess it's very straightforward, right? Once you know what's the the constant, like what's the expression for H9, in principle, of course, you can work out everything, right? So in the expression for this line is P equal to P1. This is PV gamma equal to constant, and it's P equal to P2. This is also PV gamma equal to constant. You know everything is like it's like a geometry, right? So you know the expression for the line, you can calculate everything. Okay, so now we only need to calculate what is this guy in terms of the P1 and P2 and gamma. Of course, we need to use gamma So for point B and point C, they are related by this relation, which is P1. P1 P1 is okay. So let me write down here. For this point is P1 because corresponding to pressure P1. VB gamma equal to P2 VC gamma. Similarly, for A and D, you can write down P1 VA gamma equal to P2 VD gamma. So then let me copy this to here. Right. So it's from here you can say it seems it's more it's more direct. If we work with the variable V instead of T, right? But of course we know how to convert T to V because it's an ideal gas. TV equal to NKBT. So so for the C and D, okay, so oops. So we know T equal to PV divided by NKB. So we plug in one. So for TC is P2, right? Remember TC corresponding to P2, VKB minus D is also P2. And so C and D. B point and A point corresponding to P1. So now the NKB cancel out and you can factor out the P2 and the P1. So left with like this. So P2 and P1 are known. So we only need to work out this guy, but this V volume is related to the pressure through those two equations. So we only need to plug in, right? I'm pretty sure you know how to do this. And in principle, you can do this and you would get, what's the final result? Let me write down the final results first. P1 divided by P2, 1 over gamma minus 1. Okay, so to do that, we only need to, for the first equation, it's P1 to 1 over gamma equal to P2 over gamma. Right. P1 and plug in. For example, so VC, this guy, VC is P1 minus divided by P2 gamma VB from the first equation. From the second equation, we know VD is similarly P1 minus divided by P2 1 over gamma VA. Then plug those two equations to the numerator. We would get P1 divided by P2 over gamma VB minus VA. And this VB minus VA cancel out with the denominator. So left with this guy. This guy times this guy will give us the final result. Right? Yeah. So basically you just need to play with those equations, like constant pressure, adiabatic process, and also the ideal gas law. That's all you need to know to solve these kind of problems. Yeah, any questions? Okay, I guess that's all I prepared, and yeah, if you have no questions, feel free to leave. And if you have questions, you can stay here and we can discuss.
I have a question about the last part of the last problem on the second homework when we needed to graph things. And so the free energy had like ln of something minus something. So basically it could be a log of a negative number.
Right. That's I think I didn't write it down in the solution explicitly, but okay, let me. That's definitely a very good question. Okay, let me take a look at the expression. So you mean for the, okay, let me stop.
So it's ln